A large fast food restaurant is having a promotional game where game pieces can be found on various products. Customers can win food or cash prizes. According to the company, the probability of winning a prize, large or small, with any eligible purchase is 0.133. Consider your next 31 purchases that produce a game piece. Calculate the following. Note this is a binomial distribution. Round your answers to at least 4 decimal places. Since we're told this is a binomial distribution, we don't have to go through and decide whether there's a fixed number of trials, two different outcomes, and whether they're independent. We can just assume all of that and jump right into coming up with our answers. So if we want to find the probability that you win 5 prizes, we want the probability of exactly 5 prizes. So whenever you use that notation of exactly 5 prizes, we use the function Binomcdf, which takes 3 inputs. N, which is a number of trials, P, which is a probability of success, and X, which is a number of successes. So we have 31 purchases, so we're trying this game 31 times. Probability of winning is 0.133, and we want to know if we are going to win 5 times out of the 31. So using the calculator, we'll hit second, distributions, scroll down till we find Binomcdf. There are 31 trials, comma, 0.133 probability of success, comma 5. So 0.17297, which I'll just round to 4 decimals, is 0.1730. Right? What is the probability that you win more than 6 prizes? So more than 6 prizes, that could be 7 to the maximum, which is 31. Now, in that situation, you can either use Binomcdf over and over and over again, or you can use Binomcdf. In order to use Binomcdf, let's take a look at what this looks like so we understand exactly what we have to do. So here is a histogram of our binomial distribution. And the height of each bar is representing the probability given to us by Binomcdf. So if we're looking for the probability from 7 to 31, because that is what we decided our outcomes that we were interested in. I've shaded these. I've shaded them in blue. Notice that these probabilities get very small as you get past around 12 or so, which is not uncommon with binomial distributions. The sum of all of those is what we're looking for, which is 0.1087. But if you look in Binomcdf, you'll not find that probability anywhere, or in Binomcdf. You could get it with Binomcdf if you just added the bar's height 7 associated with 8, and then 9, and so forth, all the way to 31. But that's going to take an extremely long time. So what we can do, however, is use Binomcdf, which is a running total of the probabilities in Binomcdf. So 0.0120 comes straight across. But if you add 0.0570 to that, you get 0.0690. If you add 0.1331 to that, you get 0.2001. So Binomcdf is already adding those probabilities together for us. Which means if we get the sum of these white bars, which we can with Binomcdf, we just give an input of 6, and then take a complement, it would give us the sum of the remaining bars. That's the approach we're going to take. So I will use Binomcdf. The first 2 inputs are the same as Binomcdf, N and P, so 31 and 0.133. X is still our last input, but it represents where we want the sum of the probabilities to stop. So we want the sum of the probabilities to stop at 6, because if we went to 7, then that would put us into the group that we're looking for, and we want to stay out of that group. So this would be the sum of those white bars that I showed you. And if you took the complement, it would give you the sum of the blue ones. So with only one function, we can get this probability. So we take 1 minus, then go to our distributions menu, scroll down to Binomcdf. We have 31, 0.133, 6, and 0.1087. All right, what is the probability that you win between 2 and 6 inclusive prizes? All right, so between 2 and 6, this is going to get rather tricky. But between 2 and 6, we're looking for 2 to 6. I'll go ahead and list those. So I think a complement would be helpful. And one thing that we could do is, well, let's take a look at this. So 2 to 6. So our lower bound would be 2, and our upper bound would be 6. So if I show those bars shaded, that's what that looks like. So these are the ones that we want. We absolutely could just take Binomcdf with x equals 2, then 3, 4, 5, and 6, and then add those together. That would be fine. Or we could use Binomcdf to get the sum of these first two here, and then Binomcdf up to this point, and then take a complement to get these here, and then do another complement. That's getting kind of tricky. I think the easiest way would be to get Binomcdf up to and including 6, so the sum of all of these blue bars and white bars here, and then subtract Binomcdf of this smaller group down here, just up to 1. I think that's the approach I'll use on the calculator. So Binomcdf 31.133 and 6. So that's going to give me the sum of probabilities up to and including 6. But I don't want the first two in that sum, so I'm going to subtract out Binomcdf of 31.133 and 1, because 0 and 1 were those two that I don't want. Using the calculator, let's check it out. So second distributions, come down to Binomcdf, 31.133 and 6, and then minus second distribution, Binomcdf, 31.133 and 1. And we get 0.8224. Comparing that to what we had, that's exactly the correct answer. All right, next, what is the probability that you win 3 prizes or fewer? So 3 prizes or fewer. So that would be 0 to 3. So that's what we're looking for. The nice thing is if you start the counting with 0, then Binomcdf will get that result for you directly. So 31 is n, 0.133 is p, the last input is going to be 3, and it will add together the probabilities associated with 0 outcomes, 1, 2, and 3, and give us what we're looking for. So second distributions, come down to Binomcdf 31.133 and 3. So 0.3946.